Hello students, good morning to all of you. Today I am going to discuss about the nature of the light. The introduction to this nature of the light is, according to electromagnetic theory of radiation, light is a form of energy. Any type of light is having some amount of energy. For example, white light is composed of 7 different colors, each and every color having some amount of energy. So, according to electromagnetic theory of radiation, light is a form of energy, and light is generated both in electrical field and magnetic field also. That means when a small magnet is placed in electrical field, light is generated. At the same time, when a charged body is placed in magnetic field, light is also generated. That's why according to Maxwell, the light is also called as electromagnetic radiation. That means along the path of the light, if this is the path of the light, along the path of the light, according to this theory, both magnetic field and electrical field are developed, and at the same time, according to Maxwell's theory, this light is propagated in the form of a wave like this. If this is the generation of the light in the electrical field, this is the propagation of the wave. This is crust and this is trough. If this is the electrical field, and along the path of this light, magnetic field is also developed like this. This is the magnetic field generation according to Maxwell's theory of electromagnetic radiation. That means from this diagram, a very important point is, along the path of any type of electromagnetic radiation, two fields are developed. One is electrical field, another one is magnetic field. These two fields are mutually perpendicular to each other, and these two fields are perpendicular to the path of the light also. So that means according to Maxwell's electromagnetic theory of radiation, light is generated both in electrical field and magnetic field. These two fields are mutually perpendicular to each other, and these two fields are perpendicular to the path of the light also. Now, this is about the theories of electromagnetic radiation. Now, there are two theories here. There are two theories. Now, the theories of electromagnetic radiation. There are two theories. One is wave theory of light, and the second one is corpuscular theory of light. The wave theory of light is proposed by Huygens. According to him, the light is propagated in the form of a wave like that. Along the path of the light, both electrical field and magnetic field are developed. These two are mutually perpendicular to the path of the light also. And according to this theory, there are so many types of electromagnetic radiations. Among them, the very important types of electromagnetic radiations are gamma rays, X-rays, ultraviolet rays, visible radiation, infrared radiation, microwaves, and radio waves. That means among these various types of electromagnetic radiations, Gamma rays possess more amount of energy. That's why they are more harmful radiations among various types of electromagnetic radiations, and UV and IR radiations are emitted from the sun. And very important type of electromagnetic radiation is visible radiation. That light is visible to our eyes. For visible radiation, wavelength range is 3800 angstrom to 7600 angstrom. For violet light, wavelength is 3800 angstrom. For red color, wavelength is equal to 7600 angstrom. And after that, the microwaves are used in radar system. Radio waves are used in the FM radio stations. So these are the various types of electromagnetic radiations. You should remember various types of electromagnetic radiations and their energy order also. So this is the decreasing order of the energies of various types of electromagnetic radiations. Now, according to Huygens wave theory of light, the light is propagated in the form of a wave. Along the path of the light, both electrical field and magnetic field are developed. These two fields are mutually perpendicular to the path of the light also. These two fields are mutually perpendicular to the path of the light also. Now, the next one is, what are the various properties of the light? What are the various properties of the light? And various properties of the light are, the main characteristic property of the light is, one of the very important characteristic property of the light is wavelength. It is defined as the distance between two nearest crusts or troughs is known as wavelength. So wavelength is defined the distance between two nearest crusts or troughs is known as wavelength. Now this is the representation of the wavelength. This is known as wavelength. The distance between two nearest crusts is known as wavelength. Now this is about the various characteristic properties of wave motion of the electromagnetic radiation. One of the very important characteristic property of wave motion of the electron is wavelength. Wavelength is defined as the distance between two nearest crusts or the distance between two nearest troughs. This is crust and this is trough. Height is crust, depth is trough. So the distance between two successive crusts is known as, or the distance between two nearest troughs is also known as a wavelength. So this is very important characteristic property of wave motion of any type of electromagnetic radiation. And this is indicated in terms of angstrom unit or nanometers. 1 angstrom is equal to 10 power minus 8 centimeters. 1 nanometer is equal to 10 power minus 7 centimeters or 10 power minus 9 meters. 100 centimeter is equal to 1 meter. So generally the wavelength of any type of electromagnetic radiation is expressed in terms of either angstrom unit or nanometer. 1 angstrom is equal to 10 power minus meters or 10 power minus 10 meters, and it is also expressed in terms of nanometer. 1 nanometer is nothing but 1 millimicron, 1 mu. 1 nm nanometer symbolic representation is, it is equal to 10 power minus 7 centimeters or 10 power minus 9 meters. So the wavelength of, for example, the wavelength of violet light is 3800 angstrom unit. That means generally wavelength of any type of electromagnetic radiation is expressed in angstrom unit, and very important significance of this wavelength is wavelength and energy are inversely proportional to each other. Remember that this is very important point in the characteristic properties of motion of any type of electromagnetic radiation. Shorter the wavelength, energy of the radiation is more. Longer the wavelength, energy of the radiation is less. For example, in the case of visible light, for red color, lambda is more, which is equal to 7600 angstrom. So for red color, energy is less. In the case of violet color, lambda is equal to 3800 angstrom. So for violet color, the energy of the radiation is more. So this is about the first characteristic property of wave motion of the electron. Once again, these are the very important points about the wavelength of the electromagnetic radiation. Generally, the wavelength of any type of electromagnetic radiation expressed either in angstrom unit or in nanometers. Now the next one is frequency. Frequency. It is defined as number of waves passing through a particular point in 1 second. How many waves are passing through a particular point? This is the wave propagation of the one of the type of electromagnetic radiation. So it is defined as the number of waves passing through a point in 1 second is known as frequency. It is represented by the symbol nu, N-U-E, nu, and the unit of frequency is how many number of waves are passing through a point in 1 second. That's why second inverse is the unit of the frequency. It is also expressed in terms of hertz, scientist name hertz. 1 hertz is nothing but 1 CPS. So the frequency of any type of electromagnetic radiation is expressed in terms of hertz, CPS or second inverse. So the frequency is defined as number of waves or cycles, both are same, passing through a particular point in 1 second is known as frequency. And very important point is frequency and wavelength are inversely proportional to. That's why frequency and energy are directly proportional to each other. And very important point is frequency and wavelength are inversely proportional to each other. That means nu is equal to C by lambda. This is not E. Please correct that one. Nu is equal to C by lambda. That means lambda and frequency are inversely proportional to each other. That's why energy and frequency are directly proportional to each other. So this is about the frequency of the one of the type of electromagnetic radiation. And then completion of frequency. The next one is wave number. Third characteristic property of the one of the type of electromagnetic radiation is wave number, and the wave number is defined as the number of wavelengths per unit length. The number of wavelengths per unit length is known as wave number. So the formula used to calculate wave number is reciprocal of the wavelength. Nu bar is equal to, nu bar means wave number of the one of the type of electromagnetic radiation. This is not nu, this is nu bar. Nu bar is equal to 1 by lambda. That means the reciprocal of the wavelength. Once again I will repeat the statement of wave number of the any type of electromagnetic radiation. The number of wavelengths per unit length. That means reciprocal of the wavelength in centimeter is nothing but wave number. So the formula used to calculate wave number, that means nu bar is equal to 1 by lambda in centimeter or 1 by lambda in meter. So the unit of wave number is centimeter inverse or meter inverse. So the used to calculate the wave number of any type of electromagnetic radiation is nu bar is equal to 1 by lambda. And other important characteristic property of any type of electromagnetic radiation is velocity of the light. It is defined as the distance covered by a wave in 1 second. The distance, how much distance was covered by a particular type of electromagnetic radiation in 1 second. That's why the unit of the velocity of the light is either centimeter per second or meter per second. Its formula to calculate velocity of the light for any type of electromagnetic radiation is, it is the product of frequency and wavelength of the electromagnetic radiation. Very important in this definition is, from radiation to radiation, wavelength and frequency of the radiation varies, but for any type of electromagnetic radiation in vacuum, the velocity of the light value remains constant. Its value is 3 into 10 power 10 centimeter per second or 3 into 10 power 8 meter per second. So very important point is, there are so many types of electromagnetic radiations: gamma radiation, X radiation, UV radiation, visible radiation. If you take any type of electromagnetic radiation, for each and every type of electromagnetic radiation, the product of frequency and wavelength remains constant. That it is one of the universal constant. That means velocity of the light remains constant for any type of electromagnetic radiation. For example, for red color, velocity of the light value is 3 into 10 power 10 centimeter per second. For UV light also, velocity of the light is 3 into 10 power 10 centimeter per second. That means from radiation to radiation, wavelength and frequency or wave number varies, but not the velocity of the light. Please remember this point. And next one is amplitude. Amplitude means the height of the crust or depth of the trough. The height of the crust, this is the meaning of height of the crust or depth of the trough is known as amplitude. So the amplitude determines the intensity or brightness of the light beam. The last characteristic property of the wave motion of any type of electromagnetic radiation is amplitude. Amplitude means height of the crust or depth of the trough. If the height of the crust is more, intensity or brightness of the light beam is also more. That's why generally amplitude is expressed either in centimeter or meter. Now, up to now, Huygens wave theory of light, that means according to Huygens wave theory of light, light is propagated in the form of a wave. Wavelength, frequency, wave number, velocity of the light, amplitude are the characteristic properties of the wave motion of the electromagnetic radiation, and this is corpuscular theory. Corpuscular theory of light is proposed by Newton. According to him, light is composed of large number of tiny particles, large number of smaller particles. Tiny means very small. Each and every type of electromagnetic radiation consists of very large number of tiny particles. These particles moves in straight lines but not in the form of a wave. That's why this corpuscular theory failed to explain the properties of the various types of the electromagnetic radiations. So this is the another way of expressing the electromagnetic spectrum. The electromagnetic spectrum is defined as the arrangement of various types of electromagnetic radiations in the increasing order or decreasing order of their wavelengths or frequencies or wave numbers or energies is known as electromagnetic spectrum. This is one of the example of electromagnetic spectrum. Gamma rays, X-rays, UV rays, visible radiation, IR radiation, microwaves radiation. So here various types of electromagnetic radiations are arranged in the decreasing order of their energies. The energy of gamma rays is very high because its lambda is very negligible, equal to 1 angstrom. For X-rays, the maximum limit of lambda is 150 angstrom about. So that means from left to right, the energy of the various types of electromagnetic radiations decreases. So this is also nothing but the electromagnetic spectrum. So once again, the electromagnetic spectrum is defined as the arrangement of various types of electromagnetic radiations, either increasing order or decreasing order of their wavelengths or frequencies or energies is known as electromagnetic spectrum. This is also one of the example of electromagnetic spectrum. When white light is allowed to pass through a prism and that white light dispersed in 7 different colors, Vibgyor, violet to red. This is also one of the example of the electromagnetic spectrum. That whole setup is known as spectroscope. The spectroscope means it is used to observe the spectrum. So this is about the various theories of electromagnetic radiation. Now, based on various characteristic properties of the wave motion of the electromagnetic radiation and calculate or solve the frequency, wave number of the light whose wavelength is 400 nanometers. For example, if you know the lambda value of any type of electromagnetic radiation in various units, it is possible to calculate its frequency and wave number with the help of this formula. the velocity of the light c is equal to, velocity of the light is nothing but product of frequency and wavelength of the radiation. So c is equal to nu into lambda. Apply this formula to calculate frequency if you know the wavelength of the radiation in different units. That means this is nothing but the product of these two is nothing but velocity of the light. Therefore nu is equal to c by lambda, both are same, or lambda is equal to c by nu. So this is very important formula to calculate the frequency, wave number, wavelength. Among these three, if you know any one of these three, it is possible to calculate other two by using this expression. And other formula in this topic is reciprocal of the wavelength is known as wave number. Wave number means number of wavelengths per unit length area. So the formula used to calculate of any type of electromagnetic radiation is 1 by lambda in centimeter or meter, and this is nothing but lambda is equal to c by nu. Substitute this here. Now this will becomes nu bar is equal to nu by c. So these are the very important formulas in characteristic properties of wave motion of the electromagnetic radiation. Now solve this problem. In this problem, lambda is given. In this problem, lambda is equal to 400 nanometers. Very important point is 1 angstrom is equal to 10 power minus 8 centimeters. 1 nanometer is equal to 10 power minus 7 centimeters. Now first convert nanometers into centimeters. If they give in angstrom, 1 angstrom is equal to 10 power minus 8 centimeters. So first convert nanometers into centimeters by using this conversion. So which is equal to 400 into 10 power minus 7. This is equal to 4 into power minus 5 centimeters. So 400 nanometers is equal to 4 into 10 power minus 5 centimeters. So each and every student should remember how to convert the nanometer into centimeter. 1 nanometer is equal to 10 power minus 7 centimeters. Now apply the formula to calculate frequency. So frequency is equal to c by lambda. This is equal to value of c in CGS system is 3 into 10 power 10 divided by lambda is equal to 4 into 10 power minus 5. Therefore, this is equal to 3 by 4, 0.75 into 10 power into 10 15. This is the frequency. That's why frequency is expressed in second inverse or H or CPS. So if you know the lambda value, it is possible to calculate its frequency and wave number also. So once again I will repeat the solution. Nu is equal to c by lambda. First convert the lambda into centimeters by using this conversion. 1 nanometer is equal to 10 power minus 7 centimeters. Therefore, nu is equal to c by lambda. So, the frequency of the radiation whose wavelength is 400 nanometer is equal to 0.75 into 10 power 15 second inverse. At the same time, it is calculate wave number of the radiation also. There are two formulas. Wave number nu bar is equal to 1 by lambda, nothing but nu by c, both are same. So, now calculate the wave number of the radiation. Formula is 1 by lambda in centimeter. Therefore, 1 by lambda in centimeter is 4 into 10 power minus 5. 4 into 10 power minus 5. Therefore, wave number is 1 by 4, 0.25 into 10 power 5. Wave number unit is 1 by centimeter or centimeter inverse. So, if you know the lambda value, it is possible to calculate frequency and wave number. Very important formula is the product of wavelength and frequency of any type of radiation remains constant. From this, it is possible to calculate frequency or lambda. The reciprocal of the wavelength in centimeter or meter is equal to wave number. This is nothing but nu by c. So, this is the way of calculation of frequency and wave number of the light whose wavelength is given. Now, in the second problem, calculate the wavelength and wave number of whose frequency is given. If you know the frequency, it is possible to calculate its wavelength and wave number also in the similar way. Here, in the second problem, frequency is given, which is equal to 40,000 Hz or CPS, 40,000. That means 4 into 10 power 4 Hz, 10 power 4 Hz. Now calculate the wavelength. Calculate the wavelength. Lambda is equal to c by nu. That is equal to 3 into 10 power 10 centimeter per second divided by frequency 4 into 10 power 4. And this is equal to 0.75 into 10 power 10 into 10 power minus 4, that is equal to 10 power 6, that is equal to 10 power 6 centimeters. So from frequency, lambda is equal to c by nu. C is expressed in centimeter per second. Frequency is expressed in second inverse. That's why lambda, the unit of lambda is centimeter. Suppose if you want to convert the lambda into angstrom unit in centimeter, this value is 0.75 into 10 power 6 centimeters. If you want to find out the wavelength of the radiation in angstrom unit, convert the centimeters into angstrom by using this conversion. 1 angstrom is equal to 10 power minus 8 centimeters. If you want to calculate the wavelength of the radiation in terms of angstrom unit, convert the centimeter into angstrom. 10 power minus 8 centimeters is equal to 1 angstrom. Therefore, 0.15 into 10 power 6 centimeters is equal to how many angstroms? So, this is equal to, therefore, this is equal to, lambda is equal to, this much centimeters is equal to 1 angstrom. 0.75 into 10 power 6 centimeters is equal to how many angstroms? Apply cross multiplication. This into this divided by this gives the answer in angstrom unit. That means 0.75 into 10 power 6 divided by 10 power minus 8. Therefore, lambda in angstrom unit is equal to 0.75 into 10 power 6, 10 power 8, 10 power 14 angstrom unit. So, this is the conversion of centimeter into angstrom unit. Suppose if you want to convert the centimeter into nanometers, apply this one. 1 nanometer, nothing but 1 nanometer is nothing but 1 millimicron. 1 millimicron is equal to 10 power minus 7 centimeters, both are same. 1 nanometer is nothing but 1 millimicron, M-I-C-R-O-N, micron. 1 micron value is equal to 10 power minus 7 centimeters. Therefore, if you put the centimeters into nanometers, 0.75 into 10 power 6 divided by 10 power minus 7 gives the lambda in nanometers. Here in the first problem, lambda is given in microns, mu. Note down the conversion between micron and centimeter also. While doing this problem, you should apply 1 micron is equal to 1 micron is nothing but 1 micrometer, both are same. This is millimicron, follow properly. 1 nanometer is equal to 1 millimicron. This is micrometer, micron. That means wavelength is expressed in centimeter or meter or angstrom unit or nanometer. Nanometer is nothing but millimicron. Remember that. Another representation also you should remember. It is also expressed in the form of micron and micrometer, both are same. 1 micrometer is equal to 10 power minus 4 centimeters. After that, 6 microns means 6 into 10 power minus 4 centimeters. After that, calculate the frequency and wave number. So, here while doing the problems based on characteristic property of wave motion of the electromagnetic radiation, each and every student should remember what are the units of wavelength. How to convert the angstrom into centimeter, nanometer into centimeter, micron into centimeter. You should remember compulsory. And very important formulas used in this topic is the product of frequency and wavelength is equal to velocity of the light. 1 by lambda is equal to nu bar. Nu by c is equal to nu bar. Now the next topic in atomic structure is Max Planck's quantum theory of radiation. According to Max Planck, when an iron rod is heated in a furnace, first it turns to dull red color, and then if you increase the temperature, that dull red color becomes more and more red color. After that, if the temperature is further increased, now that red color becomes white color. If we increase the temperature very high, finally that white color becomes blue color. That means the origin of this quantum theory, according to Max Planck, indicates as the temperature increases, the frequency of the emitted radiation goes from lower frequency to higher frequency. Very, very important point is, according to Max Planck, when the temperature increases, the frequency of emitted radiation by a body goes from a lower frequency to a higher. That means for visible light, lambda for violet light is 3800 angstrom. For red color, lambda is 7600 angstrom. In the first stage, the color is a red color. That means for red color, lambda is more, so frequency is less. Nu is equal to C by lambda. So if the lambda is more, means frequency of that radiation is less. So when temperature increases, the frequency of the radiation emitted by a body changes from lower frequency. This is lower frequency because lambda is more. And finally that iron rod turns to blue color. So when compared with red color, for this blue color, lambda is less. Lambda is less means frequency is more. So according to Max Planck's quantum theory, as the temperature increases, the frequency of the emitted radiation goes from lower frequency to higher frequency. Based on this origin, this theory successfully explains black body radiation. The difference between ordinary body and black body is, if the light falls on any ordinary body, if the light, any type of light falls on ordinary body, some part of that light is absorbed by that body and some part of light is reflected from that body and some part of the light is transmitted through this body. That is the property of an ordinary body. If the same light falls on a black body, which body acts as a black body? A hollow metallic sphere, coated inside with platinum black color, a hollow metallic sphere coated inside with black color, with small opening, with small hole on the walls, nearly acts as a black body. If the same radiant energy falls on this type of black body, that body completely absorbs the incident radiation, and that body also re-emits the absorbed radiation perfectly. That means a black body acts as perfect absorber. That body absorbs all the incident radiation, and it also re-emits the absorbed radiation through small aperture, that means hole, opening. That is the application of a black body. Very important point is Max Planck's quantum theory successfully explains the black body radiation. A hollow metallic sphere coated inside with the platinum black color with a small opening nearly acts as a black body. The property of black body is it acts as perfect absorber and perfect re-emitter of the absorbed radiation. Remember that there is no transmission and reflection. Black body absorbs completely the incident radiation, and it also re-emits the absorbed radiation perfectly. That is the property of the black body. So this theory explains the black body radiation only. And very important point in this theory is the radiation emitted by a black body depends upon temperature. This is very important point in IIT JEE main type of examinations. According to Max Planck's quantum theory, the radiation emitted by a black body depends upon temperature. That means when temperature increases, the maximum intensity of the radiation emitted by a black body shifted towards shorter wavelengths. That means at shorter wavelengths, the energy of the radiation emitted by a black body is more. So when temperature increases, the radiation emitted by a black body, the maximum intensity of the radiation emitted by a black body shifted towards shorter wavelengths, means at shorter wavelengths energy of the radiation is more. That means energy of the radiation is directly proportional to frequency of the radiation according to Max Planck's quantum theory. So this is very important point. And in this slide, the effect of temperature on the emission of radiation by a black body is at 3000 Kelvin temperature. If the graph is drawn between wavelength of the radiation versus intensity of the radiation, wavelength of the radiation versus intensity of the radiation, this peak is formed like this. One peak is formed like this. That means when wavelength increases, the radiation emitted by a black body, the intensity of the radiation emitted by a black body is also increases to a certain maximum and then decreases. Now here at this lambda, that means say lambda 1, the intensity of the radiation is more at 3000 Kelvin temperature. If we increase the temperature from 3000 Kelvin to 4000 Kelvin, now this is the peak. That means the maximum intensity of the radiation is shifted towards shorter wavelengths. At the beginning, wavelength value is less. So in the second case, that means if we increase the temperature from 3000 Kelvin to 4000 Kelvin, maximum intensity of the radiation emitted by a black body shifted towards shorter wavelengths. That means shorter wavelengths intensity of the radiation is, that means energy of the radiation is more. If we increase the temperature further, that means at 5000 Kelvin temperature, now this is the maximum intensity of the radiation and corresponding lambda value is here. That means when temperature increases further, the maximum intensity of the radiation emitted by a black body shifted towards shorter wavelengths, that indicate at shorter wavelengths energy of the radiation is more. Therefore, the energy of the radiation is directly proportional to frequency of the radiation. So, very important point is the radiation emitted by a black body depends upon the temperature. When temperature increases, the maximum intensity of the radiation emitted by a black body shifted towards shorter wavelengths. So based on this origin, he proposed 4 assumptions. Max Planck proposed 4 assumptions. First assumption is, light is a form of energy. It is already known to you. White light is composed of 7 different colors. Each and every color of the light having some amount of energy. So it is already known to you. Radiation is associated with some amount of energy. And very important point according to this theory is, a black body emits or absorbs the radiation discontinuously in the form of small packets, small bundles, discontinuously in the form of small packets like this, or bundles. Each bundle is known as quanta. Very important assumption in this theory is, a black body can emit or absorb the radiation discontinuously. That's why this peak is obtained like this in this graph. And this is classical theory graph. That means the difference between classical theory and quantum theory is, according to classical theory of radiation, a body can emit or absorb the radiation continuously. That's why the shape of the graph is like this, parallel to y-axis. But according to Planck's quantum theory, a body can emit or absorb the radiation discontinuously. Remember that word is very important in this Planck's quantum theory. That's why some peak is obtained like this. So that is the main difference between classical theory and quantum theory. According to classical theory of radiation, a body can emit, absorb the radiation continuously. That is not correct according to Max Planck's quantum theory. That's why the second assumption is, a body can emit or absorb the radiation discontinuously in the form of small packets like this. Small packets like this. Each packet is known as quantum. And third assumption is the energy of the quantum is directly proportional to frequency of the radiation. Therefore, E is equal to h nu. So this is known as quantum equation. But nu is equal to c by lambda. So E is equal to hc by lambda. But 1 by lambda is nothing but nu bar. So according to Planck's quantum theory, the energy of this packet is equal to h nu or hc by lambda or hc nu bar. So this is known as quantum equation, Max Planck's quantum equation. In this equation, h is equal to Planck's constant, another universal constant. Its value in CGS system is 6.625 into 10 power minus 27 erg second. So it is possible to calculate energy of the quantum according to this theory. E is equal to h nu or E is equal to hc by lambda, E is equal to hc nu bar. H is known as Planck's constant. You should remember the Planck's constant value in CGS system and MKS system also. 10 power 7 x is equal to 1 joule. That's why 6.625 into 10 power minus 27 x is nothing but 6.625 into 10 power minus 34 joule second. Fourth assumption is a black body can emit or absorbs the radiation either one quantum of energy or whole number multiples of it. Whole number multiples of it, but not fractional values. This is known as quantization of energy. This is also very important assumption. Quantization means no fractional values. That's why the same theory was used by Niels Bohr. According to Bohr's theory, small n is equal to 1 k orbit, n is equal to 2 l orbit, n is equal to 3 m orbit, but not n is equal to 1.5. Intermediate energy states are impossible. That's why according to Max Planck's quantum theory, a body can emit or absorb the radiation either one quantum of energy or whole number multiples of it, but not fractional values. For energy states 1, 2, 3, 4 like that, but not 0 energy state, 0.5 energy state, 1.5 energy state. Those states are impossible according to Planck's quantum theory. That means according to Planck's quantum theory, energy is quantized. Quantization means no fractional. Quantization of energy means fractional energy states are impossible. That means, why? Because a body can emit or absorbs the radiation discontinuously, not in continuous manner. That's why the fractional energy states are impossible. So this is about the Planck's quantum theory. So final point is, quantum theory successfully explains the black body radiation. The same concept is applied to any type of electromagnetic radiation by Einstein. According to Einstein, both the emission and the propagation of the radiation is in the form of bundles like this. This bundle is known as photon according to Einstein. Photon is nothing but quantum. According to Einstein, a body can emit or absorb the radiation in the form of small packets. Propagation is also like that. That means both emission and propagation of the radiation is in the form of photons according to Einstein. But according to Planck's quantum theory, only the emission of the radiation is in the form of quanta, but the propagation of the radiation is in the form of a continuous wave. That is the difference between quantum theory and Einstein's theory. Once again, I will repeat the difference in between these two. According to Planck's quantum theory, only the emission of the radiation is in the form of quanta, that means is in the form of small packets like this. But the propagation of the radiation is in the form of continuous wave. That is not correct according to Einstein. According to him, both the emission and the propagation of the radiation is in the form of bundles. Each bundle is known as photon, nothing but quanta, energy packet. The energy of the quantum is nothing but energy of the photon. So final conclusion is a body can emit or absorb the radiation discontinuously in the form of small packets, and the propagation of the radiation is also in the form of small packets, but not in the form of continuous wave. So this is about the very important theory which is known as Max Planck's quantum theory of radiation.